Welcome back to STEM Online Academy. My name is Jason Masterakos. It's been a while, but I'm glad to be back. All right. So, a student asks, what steps do I use? Okay. Now, let's compare that to what a mathematician asks. A mathematician would ask, what is the structure that is controlling the system? Right? Because mathematics is about structure. All right. In today's age of artificial intelligence, right? And, you know, automation and technology and all that stuff, it's more important than ever to be thinking like a mathematician. Despite the news and everything and all of that stuff and all the fear mongering about how AI is going to be affecting mathematics, not in the way that people think. Okay. So what I'm trying to say is that in today's age, right, you need to be uh, what matters more than everything is problem solving and rigorous logical ability. Okay, that's what will matter. Okay, and in today's video, I'm going to ask some thought-provoking questions that I think are very important for you guys to understand. Okay, some of these questions will be very interesting. So here's the first one. Okay, why does right? Sorry, what does a mathematician notice before calculating? Right? What do they notice is the first thing when it comes to a problem? Pretty much, that's what I'm asking, right? Right. The calculation is good and all, but if your framework is wrong, right? If your thinking process is wrong, it doesn't mean anything. Okay, that's the point I'm trying to make. That is the whole point. All right. So that's question one. Now, question two is, why are assumptions, right, more important than actual formulas? Yes. Why are assumptions more important than formulas? Okay. Something that we should be asking ourselves, right? Assumptions are more important than formulas. Assumptions are very important, right? Actually, without the assumptions, you can't go to you can't start the problem without the assumptions. Okay, so assumptions are actually very important. Okay, without the assumptions, we all have we're not going to have a correct framework. Okay, so that's a very important thing that we need to be asking ourselves is the assumptions. All right. Question three. What does it mean to uh, control the error? Okay. Uh, and behavior and the structure. Okay. I'm going to talk about that as well in this video. All right. And question four is, why is a counterexample, right? Sometimes the fastest path to actual deep understanding of a problem. Okay. Why counterexamples are important. Now, I know a lot of you out there, depends your math background, but if you have been exposed to counterexamples, counterexamples can be frustrating sometimes to come up. I mean, to come up with a counterexample when you're thinking about something. Okay, it's not always easy. It does involve a certain amount of creativity to come up with counterexamples that work for that particular problem. Okay. Um, but even though it's difficult, it's absolutely necessary because without counterexamples, you cannot either prove or disprove an argument. Okay, so counterexamples are important. Okay. Some of us are slower than others, but it's still very important when it comes to counterexamples. All right. And then finally, question five is how do math experts use extreme cases to test whether something is true? Okay. Right. So as experts, how do we use extreme cases to test if something is true? And does the extreme case tell us the whole thing? Okay, so I'm going to be answering these questions carefully. And if you've noticed that there is a second screen, I want you to pay attention to the second screen I have. It's a simulation. Okay. So pay attention to the second screen. I'm going to rewind. Okay. So as you can see here, right, this is going to help us understand the questions. All right. We have the particular question that given a function, okay, it's not an actual function, it's a derivative of a function, right? So given the derivative of a function f prime of x, right, with the factors x minus 1 times x minus 3, okay, where x is between 0 and 4 included. We've included between 0 and 4 and an initial value condition of f of 0 equal to 2. Where does f attain its absolute maximum? Okay. Where does it obtain its absolute maximum values? Right. Now you may be thinking, how is this relevant to the question that I'm going to be answering? Sorry. Okay. It is. I'm going to explain why. Okay. Because, as I mentioned in this video, right, mathematical thinking is going to be very important in the age of artificial intelligence, right? And the way to demonstrate that is to have a technique or a system that works, a problem-solving system that can help you, not just in math, but in anything in general when it comes to problem solving, how to verify a problem, how to check for reasoning, and so forth. Right? That is what's very important in today's age, right? And what I like to use is my systems technique. I talk about it in my other videos, if you watch my other videos, okay? But I won't go into everything there. Let's just go through what I'm talking about here for new subscribers, right? So as I'm saying, stop calculating and start classifying, okay? Exactly one of the questions, right, that I was going to answer, right? What does a mathematician, right, notice, right? What does a mathematician notice before calculating? Okay, that's extremely important, right? So I'm answering that question right now, right? You need to be able to classify a problem before actually doing the algebra or the calculations right away. If you jump into the algebra and the calculations without doing any type of analysis beforehand, you more likely will be wrong. Because most math problems are much harder than the cookie cutter type of problems that you've been given in your high schools, which is just pure nonsense. Okay. So if we look at what I'm talking about in the screen, I talk about uh, pretty much a mathematician's 5-pass protocol. Okay. Step number 1, okay, or rule number 1 is you always want to translate. Okay, this is my systems technique. I've modified my systems technique. Usually it is I go from step 1, which is to visualize. Step 2 is to model. Step 3 is to execute. Step 4 is to verify. Now you can use that same technique. It's exactly the same technique, but I've translated it, right, semantically for this video, how to apply that systems technique specifically for this video when it comes to an exam, right? Because that's what our video saw, how to think like a mathematician during an exam. So step 1, we'll transform, we'll translate, visualize into translate, okay? Translate. What is given in the problem? What is being asked? Okay, you need to know what is being asked in the problem. Very important. If you don't know what's being asked, um, even if you jumped right away to a lot of you are jumping right away. A lot of you students out there, whoever you are, maybe even mathematicians who just like learning math for the sake of it, you jump to step number 4 on a hard problem. You go right to execute. You won't go right to the algebra, to calculating, and all of that jazz. Problem with that is you will more likely be wrong. You need a step-by-step system, a chronological, logical system to solving problems, right? And the only way to solve a problem is to understand it first. So translate what is being asked. What is given? What is being asked? Okay. Step number 2. the structure. What mathematical object controls the problem? Yes. What mathematical object is controlling the problem? Okay. You have to think about it, right? And what I mean by what mathematical object is controlling it, right? I mean in terms of, sorry, um, let's just have sometimes my dad tries to contact me. He's very annoying. This is making the video a little bit awkward. Bear with me though. Okay. Yeah. So two things at once. So the structure, what mathematical object controls the problem? So what I mean is it a geometric structure to the problem, right? Then you may need to approach it from a geometric point of view, right? Okay. Maybe it has to do with symmetry. Symmetry and geometry are related, though. It's not that much difference there. Maybe it's the structure is more so linguistic as it is geometric. Maybe it's more so the structure is more so about areas. That's all geometric. But yeah, maybe it's more so about parameters. Maybe it's whatever, right? You need to understand what the structure is mathematically. Okay. All right. So that's what is very important. Okay. So we've answered what does a mathematician knows before calculating? And I think we've just answered. What was the other one? Uh no. No. Yeah, we answered one question so far. But as we go through this video, I've made the video such that we're answering all the questions I'm talking about. Rule number 3, after structures, predict, right? What must be checked before calculating? Okay. What must be checked before calculating? Okay. Well, what has to be checked? Make sure you understand the problem as I mentioned. Okay. And make sure that you're organized, right? A lot of times in math, you need to be organized to do it, right? And since we're talking mainly about this, uh, especially in a logical problem, right? Most math problems are logical. But in a logical problem, you want to make sure that that your reasoning is organized. Okay, that your problem solving method is organized, like the way I have it. Okay, then you can proceed to calculating. Okay, and usually step number 4, rule number 4, I'm going to, which is to execute, either has to do with calculations or the algebra. Okay, after the prediction. All right. So do the minimum justified mathematics in order to do the execution. Okay, and then step 5, you want to verify, does the answer satisfy the question and the assumptions, right? We want to make sure that we verify what we're saying, what we're doing, what we're calculating. Otherwise, we are not real mathematicians. We're not even math students. We're some sort of numerologists. No, you don't want to be that. No, that's unscientific. We need to verify what we are doing. Okay? Always verify the results. Don't just calculate, make sure you're making sense out of what's being asked. Okay? So we answered question 1. What does a mathematician know before calculating? All right. Now, as we go through this video, there's some other stuff. As I said, with the translate, right? I'm giving you an example. Given f prime of x, right? As I mentioned, f prime of x was that factored problem, right? Go back here, f prime of x is x minus 1 times x minus 3, where x is between 0 and 4 included, and f of 0 is equal to 2. Okay, so given f prime of x, right, we know our interval is included in 0 and 4, and we know our initial condition is f of 0 equals 2. So the translated part here, right, for step 1 would be to ask where f is largest, right? Okay, you want to ask where f is largest because we're looking for the absolute maximum, right? Absolute maximum, absolute min. We want to know where f is either largest or smallest, right? So when it comes to the translation part, we want to take the question that was being asked and translate it, figure out what the implication of that question is in words. And then when we know the implication of that in words, we can go about a plan of attack. Okay, so that's what's very important when it comes to doing problems like this. Okay, now I do want to answer, uh, as it says here, right? Translate the words before choosing a method, right? Question number 2, which is why are assumptions more important than formulas? Okay, why are assumptions more important? Okay, I don't really go through that in the video. Okay, but the video will play a major role in a lot of these a lot of the other questions. So why are assumptions more important than formulas? Well, because assumptions, right, tell you where to start. Okay, they tell you where to start, right? They give you a framework of how and where to start. Without the framework, you don't have a way of solving anything. Okay, so you have to have assumptions. That being said, though, you don't base your final results purely only on the assumption. Aha, that's a very good question. When it comes to calculus, when it comes to logic, when it comes to anything in mathematics, but even in reasoning in general, right? Logic in general, you want to make sure that yes, you start with assumptions, but you need to prove rigorously, airtightly, based off those assumptions. If you just take the assumption and you only take that assumption as is, right, as your results, getting to your result, then you will be wrong. Okay, so be careful what I mean by assumptions. All right. Question number 3: what does it mean to control error, behavior, structure, and etc.? Okay, what does it mean to control that? What does it mean to control error, behavior, and structure? I'm going on to the next part, by the way, in answering this question, but also the second part of my systems technique, part 2, the structure, because that's convenient for this question, right? Because what does it mean to control behavior, structure, and etc. Right? Now, as you can see here, I've graphed the function. It's very important if you graph things, right? So you can see what is happening. Okay, so here's the graph of f prime of x. Okay, you can see that based off the concavity, it's concave up. We're doing a first derivative test on f prime of x, right? It's important to do that where we know where f prime is greater than 0, and so forth, or where f prime is less than 0, but here where f prime is greater than 0. So we can do a first derivative test, right? And we know our derivative sign and behaviors of f, right? So I'm pretty much answering the theory question. What does it mean in terms of control, error, behavior, or structure? Well, here we're mainly looking at the behavior. Mainly in this question, it's about the behavior of this structure that's important. All right. So for you students out there, right, behavior slash structure is very important when it comes to analyzing a problem like this when you're looking at absolute maximums or absolute minimums. Okay. Right? And you can see not only the behavior, but it's important to notice the factored form. We got the roots of it at x equals 1 and x equals 3, right? So we plotted it right there. Okay, and we see the behavior as follows. Behavior of f. Okay, from the first derivative test. So in answering that question, we're moving on to step 4. Question 4, sorry. Sometimes I feel like I chew my words. Question 4. What does it mean to have a counterexample? Did I say what? No. Why does a counterexample? Sorry. Why does a counterexample sometimes, you know, sometimes the fastest thing to understanding, right? Why are counterexamples sometimes the fastest way of understanding? Okay. So I want you not to pay attention as much to the video right now, but it is very important for mathematics in general to understand what I mean by counterexamples. Okay. I'm saying not to pay attention right now because this problem doesn't require counterexamples. But it's still a very good example because it hits most of the points of the questions I want to ask. Okay, so what is a counterexample? Right? Why is a counterexample sometimes the fastest way for understanding? Why is that? Because a counterexample tells us, right, if a form of reasoning is airtight. If you can find one counterexample into any mathematical argument, right, any mathematical argument, at least one, right, at least one counterexample, it falls apart. The whole thing falls apart. Mathematics has to be airtight. This is not an look. I don't want to say that I'm selling you the God's gift system for solving all of mathematics. I'm not. But I am making it easier to reason. That's what I can guarantee you is that my methods have a way to make it easier for students of all sorts to reason better or learn how to reason if you haven't learned to reason. Okay, uh, but counterexamples is a form of reasoning that if you when you use when you come up with a counterexample for any argument, if you find a counterexample, automatically that argument is disproved as long as you can prove that counterexample. Okay. And it's a much faster way to understanding for that reason because it doesn't require you to have some formula to develop the counterexample, right? All you need is to think creatively, right? Think creatively, and that will think creatively. What I mean by that is think creatively and be able to prove it, right? That can and it can be it can be much faster than using formulas for understanding because formulas, first off, they take a long time. Well, they're easy, but sometimes the algebra is just too long and it's ridiculous, right? Um, so that's one thing. And the counterexample leads you to an intuitive understanding as well. So intuitive understanding and a faster, more creative approach, a deeper approach to understanding if something is true or false, right? Okay. All right. So let's watch the rest of this video I have here. I like to have simulations. I feel like that they help students understand what's going on when it comes to math. Yes, the panic mode step, right? I don't want to say panic mode. Where are we? Execute. We're in the execution phase. Yes, executing our original problem, right? The f prime, right? F prime of x was x minus 1 times x minus 3, where x is between 0 and 4 included, and f of 0 is equal to 2. Okay? So here you can see, right, that I've automatically went into a bit of a frenzy. We're on step number 4. Number 3. The execution step. Step number 3. Execution. Okay? So as you can see here, yes, you can see right here that I have went a bit mile over it, right? Where are we? Where are we? Yes, execution, right? Where we're looking now, this is where we're applying our logic, we're applying our reasoning to a problem, for instance, right? Okay. Step number 4, right? We want to verify. Right? Review it. Oh no, step number 3. Sorry. Step number 3. I'm just trying to retrace my steps. Step number 3. We're looking at the executing. Executing in this sense, right, is to predict the candidates of the problem, right? I said predict instead of execute. Okay. So we're looking at an absolute maximum on a closed interval, right? That's what we're trying to do. So obviously you check for critical points, check for endpoints. That's how you determine the absolute maximum, right? Okay, so as you can see here, I have my roots, my critical points. But by the way, the critical point was already determined. Once you have the factors of x for f prime, substitute them in to your f prime function. They already gave that to us. And once we have that, we can determine a maximum or minimum. That maximum or minimum is not the absolute max or absolute min of those critical points. We have to figure out the absolute highest. Okay. All right. So as you can see here, right, what I have. Okay, and then we move to step number 4. Still going through step number 4, right? So we're still going through the execution phase. Okay. Right. So still going through my mathematician's 5-pass protocol, right? So we're looking at f prime of x squared minus 4x plus 3 at f of 0 equals 2. Now, remember what the question is asking, right? What was it asking? Where does f attain its absolute maximum? Where does it attain its absolute maximum for f prime of x being x minus 1 times x minus 3, where x is between 0 and 4 included? Where does it attain it? I want you to think about that for a moment. Where does it attain it? You calculus students out there, I want you to interact with me. Give me something, right? In the chat. You can either dispute or come up with your own conclusions. Where does f attain its absolute maximum? To get an absolute maximum, right? Hint, hint. Why did I go from f prime of x to f of x? Aha, because the critical points aren't enough. Okay? The critical points are not enough. The critical points, valuing the critical points that were given to us from our f prime of x, only is going to tell us a maximum or minimum. In this case, a maximum, because we're dealing with absolute maximum. But it doesn't tell us the absolute maximum. To get the absolute maximum, we need to get the original function f of x. And to get the original function f of x, we would have to not differentiate, integrate. All right? Because we want to get those endpoints. We don't just want critical points, we want endpoints. Evaluating those roots, those values of x that we had in the parabola that we had earlier, okay? And substitute them into the original function. But the only way to do that is to integrate back to the original function. So as you can see here, I went from x squared, integrating that to x cubed over 3. For x becomes minus 2x squared plus 3 becomes 3x, right? And yes, as you can see here, right? And I've made a table. Make sure you make a table, right? At x equals 0, we get our f of x at an endpoint, right? So as you can see here, I'm comparing the local max, local min, and endpoints, right? At x equals 0, we substitute x equals 0 into our original function. Okay, we should get f of x being 2. That's an endpoint. Okay. We're using the original initial value of f of 0 equals 2 in our original function f of x. We need to get the endpoints. Okay. At x equals 1, right? So we want to go throughout the entire interval, right? Because our interval was closed from 0 to 4. So we're going from x equals 0 to x equals 4 is included. So we start at x equals 0, we got an endpoint. At x equals 1, okay, pay attention, right? At x equals 1, all right, we got f of x to be 10 over thirds. That's what will happen, right? Sorry. So you can see that we're getting a local, at x equals 1, we will get a local maximum of 10 thirds. At x equals 3, we're going to get f of x being 2, a local min. And then we get x equals 4. At x equals 4, f of x should give us 10 thirds, another endpoint. Okay? So we know where our endpoints are and our local max, local minima. Okay? And then based off those, we can determine what our absolute maximum or absolute minimum actually is. Okay? So like I said, in a world, right? Because our world is becoming really weird lately. In a world where we have AI, in the AI era, having a system is very important. A step-by-step system to help you solve hard math problems, right? Yes. So, and I want to be able to help you guys, just like how this system helped me um, get stellar grades in university. Okay. Now, I'm not saying a lot of you will be able to do that, but I can definitely help improve your education, uh, outcomes much better than actually what the schools are teaching, because what the schools are teaching is not helping you. It's setting you up to fail. Okay. So if you feel like that this video gave you some deeper insight, please like and subscribe, right? New viewers, like and subscribe. It always helps. Um, so that would really help the channel. And for already my viewers and subscribers already, thanks again. It's always a pleasure that you support this channel. Without you, we'd be doomed. But yes, STEM Online Academy is here, right? Uh, for one reason and one reason only, to help specifically. It's not for everybody. Uh, is to help make the next generation of mathematicians, physicists, and engineers, right? So if you are someone who needs coaching, right, needs mathematical coaching or tutoring, well, guess what? Now is a good time to start thinking about it. Back to school, uh, things are getting hectic. People maybe need help. I am always available to help level up your education, right? And again, as I said, STEM Online is here to make the next generation of brilliant minds. All right. Link in the description will be on this video below if you are inquiring about our services. All right. There's going to be plenty more videos this week. Last week I was busy. All right. Plenty more videos. Stay tuned. Things are going to get pretty interesting. All right. Thanks again, guys. Bye bye.